Well, it's nice to make a transition from being an organizer to a presenter. But before I make the full transition, I'd like to first of all thank IUTAM for their support of the conference, and in particular the organizing committee, of which we have most people here, apart from Ross Griffiths, Shigo Yoden here. We have, well, the whole committee. I'm not going to waste my whole talk on it. Peter Davidson, if you want the whole names, I can give you them later. But there's a few announcements I'll make after my talk, but I'll postpone that for now. So I'd like to talk about a new method that is really an extension of a method that began, if you like, in the 1950s and 60s in plasma physics, called the water bag model, which predates quantum dynamics. It was used in plasma physics then. And then Zabusky and colleagues in the late 70s developed a quantum dynamics method, which then was extended to what's called contour surgery, which got me into lots of trouble all my career. And then during about 10 years later, Martin Ombaum came to visit the I&I during a program, briefly in, I'm not sure which program it was actually, the balance program, perhaps in 1997 at the I&I. And we worked together for an afternoon and pieced together what was then what we called the CASL algorithm. And we both had ideas that it might work, but when we actually started coding, we realized that it was not likely to work. And we were very surprised when we actually got the speed ups and accuracy increases we found. What I'm talking about today is a further extension of the method that makes it much more robust, or if you like, more promising for applying it to many different types of problems in geophysical fluid dynamics. Its only restriction, apparently, so far, is that you need to deal with layer-wise two-dimensional flow on some kind of a material coordinate surface or a coordinate surface in the vertical. So it's using horizontal advection on these surfaces. It's of course something to do with contours because that's in the name. So let me go on. This is work with Jérôme Fontaine, a Marie Curie fellow at St. Andrews. So we know this already, that the real motion in the atmosphere and the oceans are very complex. And we're trying desperately to get better solutions to them by, for uses in, for instance, estimating climate change, et cetera, and just basic understanding of these fluids. Viscosity is negligible on these scales and down to scales that we're ever going to reach for the foreseeable future, and that makes the problem of simulation very difficult. While I'm only going to talk about the first difficulty, I think the real problem, or one of the problems, is that few methods take, oops, sorry, I'm trying to use the pointer, but I guess the pointer is this. No, it doesn't work. Ah. All right, sorry, go back to full screen. Big stick. All right. This allows me to have audience control. Okay. The key feature of this method is that we do take direct advantage of potential vorticity conservation or near conservation. It's something about the hyper-CASL algorithm that allows you to relax that conservation to deal with things like diabatic and other types of forcing in the method, which is the real advance that's taken place in recent times to make it much more robust for geophysical flow problems. And I'll illustrate at the end, assuming I don't run out of time, which at the rate I'm going probably will happen. But I'll illustrate some example, or an example of where we have a non-conservative change to potential vorticity with this new method. I won't speak about this so much today, but it has come up in the issue of balance and imbalance, and that we've been also very careful to rewrite equations in such ways that when we use potential vorticity as a prognostic variable, as they call the jargon, as a variable that we evolve directly, we are then left with the question of what other variables should we evolve alongside a potential vorticity. That's led to some very nice decompositions based on thermal wind balance, hydrostatic geostrophic balance, to try to lead to or suggest new ways of rewriting the equations that might be more efficient and accurate. Okay, I won't speak more about that though today. Okay, well, we're dealing with, at least in large-scale fluid motions in the atmosphere, we're dealing with gigantic Reynolds numbers. And this is one of the major problems that we face here. It's also the thing that keeps us all in business, I think. It's exciting to deal with high Reynolds number flows. At least I found it so. But the problem is that numerical modeling, obviously, we are faced with this problem of discretization. We are trying to seek a discrete approximation that's as close as possible to the real fluid we're trying to model. And we often not only discretize, but we also simplify the complete set of equations. So there's hierarchies of approximations that are going on here. But even once you've adopted a particular set of equations like Oberbeck-Boussinesq, you still are faced with the problem of discretization. And discretization fixes the smallest numerical scale, call it delta x, the grid spacing, say, below which there is no representation. So for instance, this is what might actually be happening below in some complex geophysical flow. So here's our grid, and what we really have below the grid is some complex turbulent sea of motion that we would hope that our discrete model can know something a little bit about, or can somehow get the collective effects parameterized. These are buzzwords that are used. We'd like to basically hope that our model gives you the average effects of this turbulence on a grid point. Of course, that's the holy grail of the field, but I don't think we're there. So we have a highly turbulent flow between grid points typically, and the question is, what do we do? Okay, so essentially the two main approaches that are taken, there's a little agreement between this, but there are two main options. One, which seems very good on the basis of it, is that you ensure all the fundamental conservation principles associated with an inviscid adiabatic flow are still satisfied in the discrete model. So you might have actually a diabatic model, but nevertheless you want to formulate the equation such that if you were solving an adiabatic, a conservative system, you might want to ensure conservation of everything you know. And the other option, which seems radical, is to completely throw away conservation, which is dangerous if you're not careful. But if you think about it, you can do this while still making a more accurate solution to your problem. So I'm going to say that most people would think that option one, which is green and therefore good, is the best one. But actually, let's look more closely and see whether that really is the wise thing. And the problem is the entropy cascade. We've heard lots about this in the last few days. We know that inviscid adiabatic fluid conserves energy in a whole host of other quantities associated with potential vorticity conservation, things called Casimirs. Could be also the area between levels of potential vorticity, they're equivalent. But these other quantities associated with this material conservation of potential vorticity are difficult to conserve in discrete numerical models due to the efficient nonlinear transfer of PV for those that are spectral to small scales, and this tends to go exponentially. But in physical space, this is due to the thinning of filaments, like in this example, where a small vortex gets sheared out and turned into a filament very quickly on the time scale of one rotation period, and the steepening of PV gradients, which is shown here, where two smooth vortices, the small vortex gets stripped of its outer levels of vorticity, leaving a very sharp edge. Both of these produce small scales in order 1 times, order 1 characteristic turnaround times.
And very non-local in wave numbers.
And very non-local, yeah. So these give you, exactly, there's a direct cascade from small to large scales, or large to small scales in these cases.
Cascade used to mean local.
That's right. So we're not stepping and waiting for it to get there, we get there right away.
Can you just make it clear which of these arguments applies to some general balance law and which would apply to the full, say, 3D equations?
The full 3D equations, including everything, contain these processes as well. As we have seen in the picture right at the beginning, where we look at the atmosphere, I think it's pretty clear that there's a heck of a lot of small-scale structure in this picture in water vapor imagery. And it's pretty clear from looking at potential vorticity through, when you calculate it with aircraft flying through filaments, that we actually see these fine-scale structures in the atmosphere. So I think it's a generic feature.
More meaning the Fjordtoft argument. More meaning the Fjordtoft argument.
Oh, the Fjordtoft argument. Okay, so that was just about there. Okay, so the Fjordtoft argument, this is a very simplified view, obviously. This is something that we can only use in these balanced, mainly probably, as far as I know, just the two-dimensional barotropic or equivalent barotropic, or the 3D quadrostrophic systems where you don't have any surface temperature gradients. Then you can use these kinds of arguments. I'm not saying this is the generic picture here, but this is an example why there's a problem, even in the simplest model. What I would say, when a lot of people have started this way, is that if you you enter the field and you say, well, what can I do? I'm not going to start with a big GCM, at least I wouldn't. I would take something simple, and I would say, well, do I understand, say, two-dimensional turbulence or two-dimensional flows? And the immediate problem you're having to deal with is the problem that you've got cascades in your model going two different ways, and you have to deal with that fundamental problem. And I think this problem is there in more complex equation sets. And of course, there's many other things too. But one can't abandon the dynamics and just say, well, the dynamics is not important, everything else matters, all these other processes are taking place. I'm going to run out of time. Okay. All right. So let me continue. So if we start, the standard picture we have from Fjortoft is that we start from energy and entropy, say peaked at some wave number initial time, then the energy tends to spread to large scales with the centroid of the energy moving towards large scales and the centroid of the entropy spectrum going to small scales. Okay, and this picture makes it pretty clear that at high wave number, you very quickly, in fact exponentially fast, it appears, drive entropy, no, I shouldn't use the word drive, so entropy goes to, escapes, what's the right word? But anyway, entropy is going to small scales at probably an exponential rate, and therefore there's no hope of ever capturing all the entropy in the model. This is why we have a problem with conserving entropy, and I think the idea of trying to build an entropy conservation in the numerical model is a dead idea now, okay, without question, although it was promoted in the past. But energy, on the other hand, since it's looking like it's going to large scales, you might think, well, we should conserve energy. And I think most people, probably if you took a majority vote in people doing numerical modeling, would say that we should conserve energy as a wholly, this is something really important to do in a numerical model. But look carefully. I mean, there's some energy spreading to small scales too.
I made the interruption. Normally energy does go to small scale.
Well, yeah, so even more so in these more complicated, so even in the two-dimensional trivial problem, if you like, a nearly trivial problem, it's not trivial, but it's one of the easiest problems here, energy's still leaking a little bit to small scales. Okay, and this is actually argued by Davidson on the shadow cascades recently, that any cascade of entropy to small scales must, at least for a while, carry a portion of the energy to small scales. Okay, we can't have that. And therefore, for a discrete model, energy cannot be conserved in numerical simulations of geophysical turbulence. We have a problem with that. Now, conserving energy is probably not going to make a huge impact, so you can probably build in energy conserving schemes, but you're also modifying the dynamics by doing that. So you have to be a little bit careful. What you really like to do is have some way of estimating how much the energy should decrease at a discrete level, and then build that into the numerical model so that you build in what all the small scales are doing. But we don't have a theory for what all the small scales are doing yet. So in CASL, effectively, sorry, an alternative approach, is there water? Sorry. Oh, yeah. Intermission. Let's see, I can speak again, good, okay. So the alternative approach that we've been following for some years now is to actually respect material conservation of potential vorticity, dq dt equals 0, to the extent possible. These are very important 4 words here, okay, because we can't do it exactly, but abandon any hope of conserving anything else, okay. So we don't explicitly conserve any global invariant in the flow, perhaps apart from linear impulse, which is a more sacred one we'll come to, but I'm not talking about that today. This is in a different context. So this,
Just if you're interested in jets.
yes, okay. All right, so this approach is what's taken in this CASL contour-advective sim of the Lagrangian algorithm, and this is in QJRMS in '97. And the idea, basically, the key idea is to use the Lagrangian representation for potential vorticity to have the best possible chance, again, this is connected with to the extent possible, to respect dq dt equals 0, which, after all, is a fundamentally Lagrangian equation. And just so I don't forget to say this, this is not a talk all about PV. It's also a talk about any other tracer, any other tracer that is nearly conserved, that one might want to follow in such models, and there are plenty of them. Water vapor is a good example. So contour advection, here's a little cartoon of it, allows one to solve the inviscid problem, or at least if you were going to simulate inviscid flow, it allows you to do this accurately and even for very complex situations. Here's a very simple situation here. And the basic discretization is over the PV levels, so we have discrete potential vorticity rather than discrete grid points, at least at the Lagrangian level. So we have patches of uniform vorticity, maybe nested like this to build up a distribution. And then we'll have, as you'll see in another slide coming up, we'll have points along the contours that represent the other dimension of discretization. So on potential vorticity contours, say capital X, a point on the contour, the potential vorticity jumps by a fixed increment delta Q, which is fixed in time. And the choice of delta Q I'm not going to go into, but this is, again, a function of accuracy, how we choose this to achieve a certain accuracy in the simulation. Now, since the contours are material, at least in the simplest application of the model, then we simply blow the contours around, if you like, by advecting them with a given velocity field. So the key problem here then is how do you get that velocity field? And we get the velocity field in this method, it's in the next transparency, but in short, that velocity field is provided by conventional methods, your favorite grid point method, spectral method, whatever you like to do, finite elements, whatever you would like to use for advection. And then the distribution of potential or contours defines Q globally, which this is what I'm saying here, that you can then use to obtain the velocity by a generalized inversion problem. So more strictly speaking, so this is what's going on. So the Lagrangian part of the code is here, where we replace this Eulerian statement by its Lagrangian equivalent over here for the contours. But then we use an Eulerian grid for inverting potential vorticity. For instance, in the simple single layer quadrostrophic case, but we do much more exotic things than this. But you might invert the Helmholtz operator on the PV anomaly here and get the velocity by two-dimensional incompressibility. But you can also deal with other non-advected quantities like wave-like quantities in shallow water equations. And then to tie these, the Lagrangian and Eulerian approach together, we use two procedures, fast filling to find the potential vorticity or a tracer on the grid given its representation on contours. And then in the reverse, we need bilinear interpolation to get the velocity on points on contours from, or we need to basically get the points on the contours, the velocity on the points on the contours from the gridded velocity field. So this is sort of what happens. We invert the velocity field on a grid like this, and we actually use a finer grid, about 4 times finer, exactly 4 times finer in each direction, to do the fast fill routine, if you like, that fills in the potential vorticity inside the region. And the use of the finer grid here allows one to get a better approximation for the circulation inside the region that's shown here. This is one contour in a simulation. And notice that if you look at things closely, you see that there are small-scale features that are way below the grid scale. So we're allowing the potential vorticity in this method to have much finer structure than velocity field, and this exploits the fact that the velocity is a smoother field than Q typically. And there are exceptions to this. Jim McWilliams yesterday talked about the frontogenesis of the surface of the ocean, and this is a case where the velocity feels rougher, and it'd be a nice challenge for the method to look at that case as well.
So I'm going to explain how you follow these particles?
Well,
Do you have to interpolate?
yeah, we have the particles themselves are moved by whatever velocity field there is, and they're connected together by cubic splines. Okay, I'm not going to go into all the details of the method, but there's a cubic spline method that's used to represent the contour smoothly. It evaluates curvature, etc.
Between more and yeah.
So here's a blow up of that little tip of a filament you saw in the previous picture, showing the actual node positions drawn on it. You can see they cluster in regions of high curvature here and here. That allows a semi-optimal representation of the contours with as few points possible. Notice that we make sure that the spacing of points on the contours are typically less than the grid spacing, about by some careful analysis. This is about the optimal way of choosing point spacing between the maximum point spacing and contours. And moreover, we limit the minimum node separation, like around these filament tips, to order delta, where delta is a so-called surgical scale. Delta X over, it turns out to be a 16th degree scale for, again, another optimized setting. Now, of course, people have asked me this for many years. What is surgery doing in these calculations, okay? In fact, it was a visit that I went down to see Charlie McCaskill about 2-3 years ago that he made me worry about this a lot, and he wouldn't let me get away until, because we were looking at two-dimensional turbulence and the decay of two-dimensional turbulence at late times, and we found that there was a problem, that in very long time simulations, where we do huge amounts of surgery like in two-dimensional turbulence, there's a accumulation of energy at large scales. We started seeing large-scale growth of the spectrum, which seemed to be anomalous. So on the one hand, surgery doesn't block the entropy cascade, or it doesn't diffuse structures. It keeps things sharp and sharp-edged vortices, which is good. And you can resolve things way below the grid size, in fact. But as I mentioned, if you excessively remove filaments over very long simulations, you see an erroneous, unphysical growth of energy at large scales in complex simulations. And essentially, the idea comes down to the fact that if you think of what one filament does, and removing it from a flow, the spectrum of a filament is actually something that has a broad range in spectral space. It looks like almost a flat function in spectral space. So every time you remove a filament, you're actually leading to a slight increase of energy at the low wave number range. So it turns out, this is what led to this new idea of hyper-CASL. The previous model was developed by myself and Martin Ombaum, where we were trying to absorb this extra error by using a pseudospectral method, but I'm not going to talk about that today. But what we do in the new hyper-CASL method is to allow an extra field alongside the contours, a so-called residual PV field, QD, which absorbs the changes in PV on the inversion grid resulting from surgery. So it's a mouthful of words to say, but what I'm saying is that if I do surgery now, and I go back and look at my field, at least the field that I would obtain from the fast fill routine, and look at the grid point PV at every point, it doesn't change at all. So surgery has no impact at grid level and above. So now surgery is completely a subgrid scale dissipation. And the advantage of that is that QD, this is what Martin Ombaum and I realized, that we can use it to implement diabatic forcing. So we can split the single equation with some source on the right-hand side, which can be rather general, into a conservative part, which we use contours for, and a diabatic part, which we are going to have a source here, which is evolving QD. So we evolve QA by contour advection, whereas QD is handled by, in this case, an array of point vortices. So we keep both aspects of the evolution Lagrangian. Contours here and point vortices here, two Lagrangian methods. Now, I see I'm probably going to run out of time. So
About 5 minutes at the most.
5 minutes at the most. So I'll probably skip all the details. What we do is we just put down a large array of point vortices at some initial time. They move around in time, and we obtained from this collection of point vortices by summing over so-called bilinear weights or Fresnel weights, the interpolations that give us basically the diabatic PV at a point. If I take a time derivative of this equation, I can actually obtain, if I know the left-hand side, which is the rate of change of QD, which is my source, I can work out then the rate of change of the circulations on the point vortices by some trick, which is essentially this equation right here. I have to invert this equation for the rate of change of the circulations on the point vortices. And again, use bilinear interpolation for these things. So we'll skip that. We just do some iteration, and convergence is rapid. We use, as a standard in this method, a fourth order Runge-Kutta scheme, but we now have a completely adaptive, so that the time step is inversely proportional to the peak vorticity at any time. And every period of time, the point vortices are put back on a regular array, so they don't get too dispersed over the grid. And this is done also automatically when the integral of some sort of what we call the twist, the maximum vorticity over time, exceeds an order 1 number. And then every time we do surgery, well, about every 20th application of surgery, we replace surgery by what's called recontouring. This is an algorithm that Martin and I developed in 2006. And this allows one to, at that stage, transfer anything that's in QD to the contours, at least to the extent possible. So we basically combine whatever's in the diabatic or the residual field with the contours at that time, put it on a very fine grid, recontour the lot, see what residual error I make from recontouring, and then I restart that residual with the error in contouring. And all these regularizations, therefore, do not change potential vorticity on the inversion grid. So it's all subgrid. So here's an example of the method, the new hyper-CASL method. This is the CASL method using a different treatment of the diabatic or the residual field, using a pseudospectral treatment of it. This is a straightforward pseudospectral code with the minimum hyperdiffusion with a del 6 operator. And this is a vortex and cell method, which is actually used in hyper-CASL as well to implement the residual field. So we carried out 4 identical simulations. They're starting from the initial same state. Time 5 is around the peak in dissipation of entropy in these methods here. Notice I'm doing only 256 by 256. I'm only showing 1/16 of the domain. 2 minutes, okay, no problem. So, well, I say no problem. All right, 64 by 64 you're seeing here in grid points. Very quickly these methods smear out. The vortex and cell is probably the most diffusive here, and we've actually quantified that.
What's the relative CPU time of those methods?
All right, hyper-CASL's about 7 times more expensive than the VIC, and VIC is the fastest. Okay, 7 times more. But it's not the relative speed; it's also speed and accuracy. Unfortunately, I don't have the diagram showing you the speed accuracy diagram. It's something we're trying to compute at the present time. But the preliminary results show that hyper-CASL is equivalent to a vortex and cell calculation done on a grid 8 times finer. And if you multiply 8 squared, you can get an idea that 8 squared over 7, it's a big speed up, okay? If you go late times then, so the time 20, you still see a lot of fine scale structure, even in a 64 by 64 box, and this is all completely washed out in these methods. It's almost, and by time 500, which we ran to, these fields just consist of 2 smooth vortices, whereas you still see a small population of vortices running around in these cases. Okay, so this is the thermal forcing case. We can do thermal forcing. I won't bother you with the details, but you basically get a jet instability, and this is a blow up at the latest time showing you the phenomenal detail with just 256 by 256 resolution, okay? So conclusions is that hyper-CASL is an efficient, accurate alternative to numerical methods commonly used in idealized, or at least to model idealized geophysical flows. But it's not limited to the QG model, the quasi-strophic model, and it's equally useful in, say, Milberbeck-Lucescu or shallow water models. And it can be extended to other things. It can be studied, as I said already, for 3D, and we can use it in a variety of geometries like we saw just before, but also channel, spherical, cylindrical. Future work, we'd like to extend the method to handle overturning stratification surfaces, and we have some ideas about how to do that, to complex 3-dimensional geometry for oceanic applications, and then add additional tracers. And I'll just leave then that image up for the end. Thank you.
So you did mention the example of front. At the front, you get a large delta function of PV, so that PV is getting much worse than velocity. How would you handle that?
Well, we're going to try to do this actually shortly, where we apply a singular symmetrostrophic model with the CASL method and see to what extent we have to modify, if at all, the settings that we currently use in terms of the various grids and their various ratios to see how well we do.
You have to allow for that sort of source.
Yes. Yes.
What's the advantage over just using a point vortex method? I mean, you're using point vortices to absorb all of your errors, but you could just use point vortex for the
You
whole,
saw that. The simulation I compared with was a straight vortex and cell method using high order well, it wasn't bicubic, but it's the Cote M4 scheme, which is considered the holy grail of the interpolation schemes in vortex methods. So we use that, and you can still see that a huge diffusion takes place in these methods.
In that method, is the vorticity conserved with each vortex during the simulation?
Yes.
It is. So that smoothing is due to some dispersion rather than...
The smoothing is due to the fact that these methods have to regrid.
Okay, but you could just have a bunch of point vortices without doing any regridding.
You could, but then that also goes crazy. There are other problems that are well known with vortex methods that if you never regrid, they bundle up and they start doing spurious coupled homeless instability everywhere. This is a well-known problem that was looked at probably 20, 30 years ago over the course of time. Regridding is essential in these methods, or else you can't keep It's the thing that kills the method, but it's needed for.
So the aim of this is to regrid with the minimum amount of smearing out.
That's right. So we regrid as least as we can in the method, and it's still that diffusive. It doesn't beat a pseudospectral method in terms of the diffusion, the apparent diffusion.
Can you explain a bit more the hyper bit? Because you said that it was arranged so that the vorticity seen by the grid was unchanged after surgery.
That's right.
I mean, surely surgery must have an impact on the large scale in the long run. I mean, when there's a vortex merger or something like that.
It does, but through the following process. The subgrid scales that are there are still having some impact later on the velocity field. So and the nice thing about the method is that it does carry subgrid scale information. And that subgrid scale information is always being fed back for the velocity advection in the method. So surgery eventually does have a role to play in terms of leading to ultimate dissipation of everything. Okay, so all the quantities that, like entropy and various moments of entropy, are going to, or potential vorticity, are going to die away because of the surgical operation subgrid scale level. So it is seen. I'm not sure that's the right answer to your question, but
I hope I've sort of finished the scientific bit now, and just like to thank